Welcome to all in the lecture series of functional analysis. Now in this lecture we have to see about the linear operators. So let's start. Let capital X and capital Y be any two arbitrary non-empty sets. Then a mapping F from X to Y is a rule which assigns the elements of capital X to a unique element Y equals to f of X in capital Y. Now here x and y both are the sets. We are taking x and y be any two arbitrary non-empty sets. Now instead of taking the set, here we take x and y both are the vector spaces. Then the corresponding mapping which we assign it as T is now an operator. So basically operator is an extension of the function. Operator is an extension of function whose domain and codomain are the parts of the vector space. This is about the operator. Now after seeing the operators, now we come to the definition of the linear operator. The definition of the linear operator is that a linear operator capital T is an operator such that the domain dt of capital T is a vector space and the range script r of t lies in a vector space over the same field. Another condition is that for all x comma y belongs to dt and the scalar alpha t of x plus y that is equals to tx plus ty and t of alpha x that is equals to alpha tx. These are the two conditions for the linear operator. That means here our linear operator capital T is the mapping from the domain script d of t to the range script r of t, and this script r of t it is a subset of y. That means here it is the domain, it is the range, and range lies in a vector space capital Y. Now here the condition for the linear operator is that the domain, that means dt, is a vector space, it is a vector space, and the range lies in a vector space over the same field. It is the first condition. Another condition is that t of x plus y it is equals to tx plus ty and t of alpha x that is equals to alpha tx. This condition is equivalent to the condition is that t of alpha x plus beta y that is equals to alpha tx plus beta ty. This is the equivalent condition for this second condition. Now after here we use the notations like that. Here we are using script d of t. This is the script d of t. It is nothing but the domain of the linear operator capital T. We use the notation for this script d of t, and this script d of t, it is always a subset of a vector space capital X. Now after this another notation is the range, that is the script r of t. This is the range of t. Now after this we have the next is a script n of t, that is called as a null space of capital T. Script n of t, it is nothing but the set of all x such that the image of the point x under the mapping T it is equals to 0. It is equals to 0, and this x is the point of capital X. This is the null space of the operator capital T. Now this domain script d of t, it is always a subspace of capital X. It is again a vector space. The range script r of t lies in a vector space capital Y for the linear operator capital T, which is from x to y. Its domain is a script D of t, which is again a vector space, and the range lies in a vector space. This is about the notations which are used for the linear operators. Now if we have the linear operator, when we are taking the mapping capital T, which is from the domain script D of t to capital Y, then we say that this is a linear operator from script D of t into capital Y. But when we are writing the mapping capital T, which is from script D of t to the range set script R of t, then this is a linear operator from script D of t onto script R of t. This mapping is always an onto map. This is about the linear operator. Now after seeing about the linear operator, now we come to the examples of linear operator. So the first example of the linear operator is the zero operator. It is an operator which gives the value 0 to each element. That means here, if T is the mapping from the vector space x to y, then for all x belongs to capital X, Tx it is equals to 0. Then this 0 operator, it is a linear operator, because for any x comma y belongs, because for any, we are writing here, for any x comma x dash belongs to capital X and alpha comma beta be any two scalar, T of alpha x plus beta y, alpha x plus beta x dash, this is equals to, as here x and y both are the element of capital X, and here capital X is a vector space, therefore it is closed with respect to scalar multiplication as well as addition, and therefore here alpha x plus beta x dash, it is again the element of capital X, and here as T is the zero operator, it means for any element of capital X, its image is equals to 0, and therefore here T of alpha x plus beta x dash, that is equals to 0, because it is the element of capital X. Also we know that x and x dash both are the element of capital X, and here we have this T of alpha x, that is again equals to, we are taking here Tx, it is equals to 0, as well as Tx dash, that is also equals to 0, and therefore here alpha Tx plus beta Tx dash, that is equals to 0, and if we are giving the name equation 1, we are giving it the name equation 2, then from equation 1 and 2, here we can write that T of alpha x plus beta x dash, that is equals to alpha Tx plus beta Tx dash, and from this we can say that the zero operator capital T, which is from x to y, is a linear operator. This is the example of the linear operator. Now here after the example of linear operator, that is the zero operator, we take another example, that is the identity operator. Now here the identity operator, Ix, which is from x to x, is defined by Ix of x, that is equals to x for all x belongs to capital X. Then clearly here Ix of alpha x plus beta y, that is equals to alpha Ix of x plus beta ix of y. We can clearly see here that the identity operator is a linear operator. Now, if we take the operator capital T from x to y, and here we are taking the vector space capital X as a function space, then for any f belongs to capital X, T of f that is equals to 1 upon f. Then in this case, if we are taking the two elements f comma g belongs to capital X, then T of f plus g that is equals to 1 by f plus g. Also here T of f plus T of g, then in this case it is equals to 1 by f plus 1 by g, and that is not equals to 1 by f plus g. Then in this case here we get that T of f plus g, it is not equals to T of f plus T of g, and therefore in this case we say that the linear operator T defined like this, T of f it is equals to 1 by f, is not a linear operator. It is not a linear operator. This is the example which is we get the example of an operator which is not linear. Now after the zero operator, identity operator, now we see another operator, that is, so here we take capital X be the vector space of all polynomials on the closed interval a comma d. Then for any x belongs to capital X, here we get x of t. This is the polynomial which we write it like this: a naught plus a1t plus a2t square up to so n plus an t to the power n, where n is greater than or equals to 1. Now x of t, it is a polynomial where t is the element of the closed interval a comma b. Now as it is a polynomial and every polynomial is differentiable, so we define the operator t on capital X like this: t of x that is equals to the ddt of x of t, and that is equals to x prime of t. As the polynomial is differentiable, so we can take t of x of t that is equals to the ddt of x of t that is equals to x prime of t. As a polynomial is differentiable, therefore this definition is well defined. Now after defining this, here t of x of t that is equals to x prime of t. Now this operator is a linear, because here when we are taking t of alpha x plus beta y that is equals to alpha x of t plus beta y of t x prime, this is equals to alpha x prime of t plus beta y prime of t, and therefore here we get that the differentiation is a linear operator. Here we are taking t of alpha x plus beta y that is equals to alpha x of t plus beta y of t prime. This prime denotes the differentiation, and it separates the constant, and therefore it is equals to alpha x dash of t plus beta y dash of t, and this is equals to alpha now x prime of t that is equals to t of x of t plus beta t of y of t, and therefore here we get that t of alpha x plus beta y that is equals to alpha tx plus beta ty, and therefore here we get that the operator t defined like this, t of x of t that is equals to x prime of t, it is a linear operator. Now also here we observe that x of t is a polynomial, and then we apply capital T, that is the linear operator on x of t, we get here x prime of t. It is again a polynomial, and therefore here we get that the t maps capital X onto itself. This is the example of the linear operator. Now after this example, we see the another example, that is, now the another example of the linear operator is an integration. Now here we take capital X equals to the function space CAB, in which every element is a continuous function defined on the closed interval a comma b. It is the set of all continuous functions defined on the closed interval a comma b. X be the set of all continuous function defined on the closed interval a comma b. Then for any x belongs to capital X, here we get x of t, that where t is the element of the closed interval a comma b. Now on this space we define the operator capital T of x of t, that is equals to the integral a to t x tau d2, a to t x tau d2. Here, as the continuous function is integrable, therefore this definition is well defined, and this integrable function is also linear operator. Now after this example of the integration, another example is again multiplication by t. In this example, again the operator t is applying on the function space CAB. That means t is applying on capital X, and here again capital X, it is the function space CAB. In this space, the operator t is defined like this: t of x of t, that is equals to t into x of t. That means the x of t, it is multiplied with t. Here again this multiplication by t, it is again a linear operator, because for any t of alpha x plus beta y, that is equals to, by using this definition, it is equals to t of alpha x of t plus beta y of t, and this is equals to t into alpha x of t plus t into beta y of t, and that is equals to alpha t x of t plus beta t y of t, and this is equals to alpha t x plus beta ty, and therefore here multiplication by t, it is again a linear operator. Now we see another example in case of elementary vector algebra. Elementary vector algebra. Now in this case, here we take the mapping T1, which is from R3 to R3. Then here the cross product with one vector kept fixed defines a linear operator like this: T1 of x, that is equals to x cross a, where small a belongs to R3. It is a fixed vector. Then in this way, the cross product of the x with one element kept fixed, it is again the linear operator. In the same way, The dot product with one fixed factor defines a linear operator, that is, again we give it the name T2, which is again from R3 to R, and it is defined like this: T2 of x, this is equals to x dot A, and this is equals to xi1 alpha 1 plus xi2 alpha 2 plus xi3 alpha 3. In this way, these two operators are the linear operators. And here in both the cases, this A, this is equals to the alpha j, it is the element of R3, is fixed. In both the case, the element A that is equals to the alpha j belongs to R3 is fixed. And here both the cross product as well as dot product, both are a linear operator with one element kept fixed. This is the example elementary vector algebra. Now we see the example of the linear operator, that is the now we see the another example of the linear operator is the matrices. Now we consider the real matrix capital A equals to alpha jk, that is equals to alpha 1 1, alpha 1 2 up to so on alpha 1 n, alpha 2 1, alpha 2 2 up to so on alpha 2 n, up to so on alpha r1, alpha r2 up to so on alpha rn, with r rows and n columns. This defines an operator capital T, which is from Rn to Rr, as y is equals to Ax, where x is equals to the sequence xi j, has n components, and y it is equals to the sequence eta j, has r components, and both the vectors are written as the column vectors. Now here we write down y is equals to Ax like this. Y it is equals to Ax. This y, it is the column vector eta 1, eta 2 up to so and eta r. It is equals to A is alpha 1 1, alpha 1 2 up to so and alpha 1 n, alpha 2 1, alpha 2 2 up to so and alpha 2 n up to so and alpha r1, alpha r2 up to so and alpha rn into xi1, xi2 up to so and xi n. That means here we are getting eta 1 it is equals to alpha 1 1 xi1 plus alpha 1 2 xi2 up to so on plus alpha 1 n xi n, and so on. In this way we are getting y is equals to Ax. Now here the operator T, which we define like this, which is from Rn to Rr, defined like this: y is equals to Ax. This operator is linear because matrix multiplication is a linear operation, and therefore matrices is also the another example of the linear operator. In this way we see the example of the linear operators, and we see also the definition of the linear operator.